Hello everyone and welcome to week 4. Pooling layer. Now this is something which we have already seen in our week 3 videos. So as we know, in a pooling layer, suppose I am doing a max pooling with a filter size or a window size of 2, a stride of 2, and I am applying a pooling on a 4x4 object, then it results in a 2x2 object. So clearly we can see that the height and the width of my input image is now decreased to half. Right? So you could see how my NH and NW is being decreased by applying a pooling operation. And as we know, in pooling operation, your convolutional neural network does not have to learn any parameters, because basically it requires only hyperparameters, which is the size of the window we will be using and the stride value. Now, of course, if we have a channel, so that means if I have an input image which has, say, a channel or depth of 10, so that means I have a channel or a depth associated with my image. In that case, we know that the resultant will have the same channel or depth as that of the input image. So it would be 2x2x10. So this would be my resultant output for a max operation. So in short, the idea of having a pooling layer is to progressively reduce the spatial size of the representation, to in turn reduce the number of parameters and computations in the network. Or in short, it is a way to perform dimensionality reduction, where you can see how my NH and NW, that is the height and width of my original input image, is now being decreased. Now, this directly have an effect on the number of parameters that my network have to learn when we move towards flattening this image to be fed into a fully connected neural network, right? So at that point, we can understand that the number of parameters which my fully connected neural network has to learn in order to perform the classification operation will be less. So that is how, even though in this particular pooling operation no parameters are learned, but still, since it is helping us reduce the NH and NW of my image, it is in turn helping us to progressively reduce the size of my image, so that when my image is flattened to be fed into a fully connected neural network, the number of parameters to be learned in that initial layers will be less. And of course, this pooling operation also helps to reduce the computation of our network. Another quite popular operation associated with a convolutional neural network is what is called as a 1x1 convolution. So let us look into what a 1 cross 1 convolution is and how it is different from a pooling operation. Now let us consider a 1 cross 1 convolution example. Now suppose that you have a 6 cross 6 image and it is a 6 cross 6 cross 1 image, that is basically a grayscale image and has no channel, and it is convolved with a 1 cross 1 filter. So it is 1 cross 1 cross 1 because of course this will be same as this, right? So in that case, our resultant output would be also again a 6 cross 6 image or a 6 cross 6 cross 1 output. And the values would be, of course, 1 into 2, 2 here, 2 into 2, 4, 2 into 3, 6, 2 into 4, 8, 2 into 5, 10, 12, and so on. Right? So this is an example of a 1 cross 1 convolution. Now, you might think that how is this going to be of use in a convolutional neural network? Because in what you see from this example is that you are just multiplying your input with a value 2. But again, this is just for this particular example I have considered. Now let us look at another example wherein which I again have a 6 cross 6 image, but this image has got a channel, say a channel of 32. Now again I am doing a convolution operation which is 1 cross 1, and again as I always say that the depth of this filter, 1 cross 1 filter, always is the same as that of the channel for your input image. So that would be 32 here. So I am convolving this with the 1 cross 1 cross 32 filter. So in this case, technically what we are doing is I have my particular image slice with its corresponding channel, right? So this is convolved with a 1 cross 1 cross 32 convolutional channel. Now this will in turn give us a result which is a 6 cross 6 image, right? So basically what we are doing is we are taking an element wise product between the 32 numbers in this particular area and this 32 numbers in my 1 cross 1 cross 32 filter, right? So this will reduce to a single integer value in my output. And of course, this has to be done for all the positions, all the 36 positions on my input image, and the resultant would be of course an image with a 6 cross 6 output. So, and of course after any convolution operation we have our activation, ReLU activation, which captures the non-linearity. So we now apply this ReLU nonlinearity to our 6x6 image. Now, there could be also another case wherein which I have similarly, say, 10 filters, right? So in that case, my resultant output would be, of course, a 6x6x10 output, right? Or it is a 6x6x number of filters. So in this case, if you have 10 filters, it would be 6x6x10. Let us now take another example wherein which you have a 28x28x192 object and you wanted to reduce that into a 14x14x192 output. So this is basically a very easy task. So what I can do is I can use a pooling operation with a window size or a filter of 2 and a stride of 2. So basically we have the equation n plus 2p minus f by s plus 1. So that is equal to n is 28 plus 2 into there is no padding. So 0 minus f, which is 2 divided by 2 plus 1. So that will basically give us 13 plus 1 equal to 14. So what you can see is that here I have reduced the height and weight of my original input, which was 22, to the height and weight of 14. So as you can see, with a pooling operation, we can reduce only the height and width of your image, right? As you can see from here, the channel or the depth of the image remains the same, 192 in my input as well as 192 in my output. So, of course, pooling is a way to reduce dimensionality, but pooling only reduces the height and width of your original input image. Now the question comes, what if I wanted to decrease the number of channels or depth in my input image? So imagine that your depth of your input image or depth of your image got to an extent where it has become very big and you wanted to shrink that depth. Now, of course, in that case, we cannot do a pooling operation, right? So imagine that you have an input 28 cross 28 and it has a channel or depth of 192. So clearly you could see here that the channel has a very large value, 192. Now suppose that you wanted to shrink this into an image of 28 cross 28 cross 32. So basically I wanted my height and width of my output image to be the same as that of my input, but I wanted to decrease the number of channels. So in this case, you cannot use a pooling operation because as we have just seen, the pooling operation only reduces the height and width of your image. So this is where your 1 cross 1 convolution comes handy. So what we can do is we can convolve this input. So I'm redrawing it. So 28 cross 28 cross 192. I have my input and I am performing a 1 cross 1 convolution operation. And I will keep the number of filters, my 1 cross 1 filter, to be 32. So I am convolving this with a 1 cross 1 filter, and of course the filter depth would be same as that of your input, which is 192. And I have similarly such 10 filters, right? So in that case, my resultant output will be, again using the equation, n plus 2p minus f divided by s plus 1. Now since for 1 cross 1 convolution we will have a stride of 1 and a filter of 1, right? So that is same as my equation n minus f plus 1. So n is 28 minus the size of my filter is 1 plus 1. So technically that gives me a value 28. So I have my resultant image, which is now a 28 cross 28 image itself. But what about the channel? So the channel of my output would be equal to the number of filters that we have used, which is 10 in this case. So my output would be now 28 cross 28 cross 10. Right? So using a 1 cross 1 filter, what you can see is that I have shrinked or I have decreased the size of the channel from 192 to just 10, keeping my NH and NW the same. Right? So basically you can use 1 cross 1 convolution to reduce the number of computation. Now another way to use this 1 cross 1 convolution is, suppose you have a 28 cross 28 cross say 192 image, and you wanted to keep the channel to be 192 itself. Now that's also fine in a 1 cross 1 convolution. So in that case I will have a 1 cross 1 convolution and I will have the number of filters to be 192. So technically what happens is my output would be n minus f plus 1, which is equal to 28 minus the size of the filter is 1 plus 1, which is 28. So my output would be again a 28 cross 28 cross the number of filters. Because it is 192, my output will also have 192 filters. Now we know that, but what is the importance of doing this? We know that after a convolution operation, it is always followed by a ReLU operation, right? So we do a ReLU operation on this 28 cross 28 cross 192, and this will help me to capture the non-linearity in my data. So if you wanted to learn more complex features by adding one more layer, then you could use this technique wherein which you have an image, you convolve it with a 1 cross 1 filter and have the number of filters to be the same as that of your number of channels in your input image. Right? So these are different ways wherein which you could use this concept of 1 cross 1 filter. So these examples make you realize what are the different ways in which you could use a 1 cross 1 convolution. So you can use the 1 cross 1 convolution to either keep the number of channels the same as like in this example, and add non-linearity or have the ability to add non-linearity into your network. Or we could use it to either increase the number of channels or decrease the number of channels. So this is a very powerful idea of that we will be using in our convolutional neural network, the 1 cross 1 convolutions.